Hello friends, so today we are going to solve 4 questions, and these 4 questions are from electrostatics, and along with the, you can say, okay, so we are going to solve these 4 questions, and these 4 questions are from our electrostatics and somewhat related to our electric potential. Okay. So the first question, we are given that find the charge density rho and the potential phi associated with the electric field shown in the figure. E is the electric field is independent of y and z. Assume phi is equal to 0, that is our potential is 0 at x is equal to 0. So basic graphical representation of electric field is given to us. So on the x coordinate, it has a magnitude between this minus a and plus a, and at x is equal to 0, it is having a maximum magnitude, that is our E naught. So in order to find out this, our charge density as well as the potential, first of all we are going to find out what will be the equation for this, you can say for the electric field. Okay. And for that we are going to make use of our basic equation of our electric field. Okay. And so we know that the derivative of electric field our derivative of our electric field is equal to charge density at a certain point x and divided by our epsilon naught. Okay. And based on this, we can further write from the graph, we can say that if we are having a constant slope of our electric field, you can say we are having a constant slope of our electric field. Therefore, we can say that our rho of x will be constant in that region. Constant in that region. And if we are having a positive slope, therefore we can say the charge density is greater than 0. And if we are having a negative slope, therefore we can say the charge density will be less than 0. Therefore, from the figure we can clearly see that in the first region, that is between our minus a and 0, our charge density is having a positive slope. Okay. And between 0 and a, it is having a negative slope. Therefore, we can write from the figure, we can say if our x lies between minus a and 0, our slope is greater than 0. And therefore, we can write that our charge density, that is rho of x, will be equal to a positive rho naught, some value. And similarly, for our x greater than 0 but less than a, we are having a slope which is less than 0. Therefore, we can say that our charge density will be our negative of our rho naught. And outside the slope, towards the left as well as right, electric field is flat. Slope is equal to 0. Therefore, we can say the electric field is equal to 0. And we can also say outside, okay, and for that we can say that modulus of x is greater than a. Under this condition, the value of electric field is equal to 0. Therefore, we can say that the charge density is equal to 0. So based on this, we can write that our you can say the charge density is going to have three values. First value will be plus rho naught, and this will be between minus a, x and 0. Second value is our minus rho naught, and that is between x and a, 0 and a. And finally, we are having 0 when the modulus of a is greater than a. So these are the value of our charge density. Now, we can easily find out value of our electric field, okay, because we have just written a relationship. This gives us the value of our electric field. So based on this, we can say that our dE upon dx will be also having the three values. First will be rho naught upon epsilon naught, and it will be lying between minus ax and 0. Second value will be minus rho naught upon epsilon naught. It will be lying between x and a. And last value will be equal to 0, which we are not bothered about. Okay, we'll just ignore it. And if we integrate it, we are going to get a value of electric field that is dependent upon our x, and it is going to give us two values. First value will be our plus rho naught epsilon naught x plus constant c1, and it will be lying between our minus a, x and less than 0. Second will be our rho naught epsilon naught x plus a constant c2, and here it will be lying between x and our a, 0 and a. Okay. Now we are interested in finding out these c1 and c2. Okay. So in order to find out this c1 and c2, we are going to use the continuity as well as the boundary condition that is going to give us value of c1 and c2. So you can say that continuity and boundary conditions. So for our continuity at x is equal to 0, continuity at x is equal to 0 because there is no surface charge at the center. So you can say no surface charge at the center. So it means the electric field or our 0 negative will be equal to electric field at the 0 positive. Therefore, from here we can say that our E naught will be equal to our, this will be equal to sorry. So this will be equal to our E naught. Therefore, from here we can say that C1 is equal to C2 is equal to our E naught. This gives us, and then we come to our the extreme edges, that is our plus A and minus A, and we know that the field, that value of electric field at plus A and minus A is equal to 0. So you can say that our field is equal to 0 at x is equal to plus minus A. Or from here we can say there is no charge outside. No charge outside. And thus we can write that from x is equal to A, x is equal to A, we get this as 0 is equal to minus, and we have this as our rho naught upon epsilon naught A plus E naught. Okay, because C1 and C2 we know is nothing but our E naught. Okay, so we can just, this value is E naught and this value is also equal to our E naught. Okay, and so we get this our minus of A. So from here we can easily find out our E naught. So with this gives us E naught will be equal to our rho naught A upon epsilon naught. Therefore, we substitute here in this equation and we get that our electric field in x direction, it is going to have three values. First will be E naught, 1 plus x upon A. Second one will be E naught, 1 minus x upon A. And third one is our 0. And first one is between our A and 0, minus A and 0. And the second one is between A and 0. And the third one is when modulus of x is greater than A. So we were able to find out the value of our electric field, or rather we can say equations of our electric field. Okay. And this equation is based on the graph which is given to us. Okay. So the graph is given something like this. Okay. So this is the value of represent electric field. So we have this as E naught, this is minus A, and this is plus A. So based on the graph, we were able to find out our what will be our value of our or various equation of our electric field. Okay. Now let us find out our charge density, and for that we can easily use our Gauss law. So we can say from Gauss law, our charge density is equal to epsilon naught derivative of electric field, and with respect to each region we are simply going to derivate it. First region is between our minus A and 0, and the value of the derivative is equal to our E naught upon A. Therefore, we get our charge density is equal to epsilon naught E naught upon A. And then we come to our second region, that is between 0 and A. We get our derivative of our electric field is equal to minus E naught upon A. This gives us the charge density is equal to minus epsilon naught E naught upon A. And outside we already know the value of electric field is equal to 0. Outside means when modulus of Ax is greater than A. And in this case, value of electric field is equal to 0. So we can say the charge density also equal to 0. Now we are also supposed to find out the potential. So you can say our electric field, because electric field is our equation in x term, so E of x will be equal to minus derivative of our potential. Therefore from here we can say that our potential is equal to minus integral of our electric field plus a constant c. Now we are going to integrate respective to the both the regions. Okay. So first region is between our minus a, x and 0. So we get this as our potential is equal to minus, and it goes from 0 to x, and our E naught 1 plus x prime upon a and dx prime. Okay. In the original equation, this term is our x, but in order to differentiate, because here we are going to substitute the limit, we have simply taken it as a x prime. Okay. That's the only purpose, like a variable. And so from here we get this as our minus E naught x plus x square upon 2a and 0 to x. Therefore we get that value of flux is our, sorry, not flux but potential is equal to our E naught x plus x square upon 2a. And similarly for our other part also, so we have our x is greater than 0 but less than a, greater than equal to. So from here you get our potential will be minus, and this is our 0 to x, and we have our E naught 1 minus x prime upon a and dx prime. So in this case, second case, we get that our potential is equal to minus E naught x minus x square upon 2a. Okay. Now we simply put x is equal to a and try to solve. So you can say that at x is equal to a, we get this as our phi of a will be equal to minus of E naught and a minus a by 2, which gives us minus E naught a by 2. And for the other end, we are having at x is equal to minus a. So the potential will be equal to our minus E naught minus a plus a by 2, which gives us E naught a divided by 2. Okay. So this is our value of our potential as well as our this electric field, charge density, sorry, we were required to find out. Okay. Next question. In this question it is given, find the electric field and the charge distribution that go with the following potential equation. Phi of x is equal to b a square minus x square for x less than equal to a, and phi of x is equal to 0 for x is equal to greater than a. And in this case, only difference between the first question and this is, here we are directly given the equation. In the first question we framed the equation based on the graph. Okay, that's a major difference. The rest of the things we have to solve it. Okay. And so first is our modulus of x is less than equal to a. Okay. Therefore we can write that our modulus of x is less than equal to a. Let us call this as our E of x at a certain point x will be equal to minus derivative of our potential. We simply substitute value of our potential equation, that is minus d of our dx b a square minus x square, and this will be coming as our 2b times x. And for our x greater than a, our value of our potential is equal to 0. So we are given that our value of x is greater than a, so we are having the value of electric field is equal to 0. So it means from here we can write that our electric field is going to have two equations based on the value of our x. First value is our 2bx when x is less than equal to a. Okay, it means the point is inside or on it, and it is equal to 0 when our x is greater than a. Okay. And next we are also find out the charge distribution. So you can say that our charge density that is our rho of x, and for that we can simply use our Gauss law, that is our derivative of our electric field is equal to our charge density divided by epsilon naught. And once again we divide this into two discussion, and the first point is when x is less than equal to a. Therefore we can say that our derivative of our electric field will be equal to, this is 2, electric field is 2bx, so this will be coming as our 2b. So based on this we can write that our charge density, here we substitute this as a 2b and multiply by our epsilon naught. So this comes as our 2b epsilon naught. So this is the value of our charge density whenever x is less than equal to a. And obviously for 0 it will be equal to 0, that is our outside. So you can see when the value of x is greater than a, we can easily say that our value of our electric field is equal to 0, so charge density also equal to 0. And we thus can say that our charge density is having two values. One is 2b epsilon naught, and this is when x is less than equal to a, and 0 when x is greater than a. And if we want to plot this charge density, we can easily plot it, and because this is independent of our x, therefore we can say that it will be lying between minus a and plus a at a certain magnitude, and this magnitude will be equal to 2b epsilon naught, and beyond that it will be equal to 0, left as well as right. So this way we can just, and we can also plot for electric field also. It is directly, you can say, like a linear. So it will be straight line passing through the origin, and negative at minus of a, okay, and positive at plus of a, and flat it will be 0 outside. Okay. Therefore we can say that, because so suppose this is our minus of a and this is our plus of a, therefore value of our this electric field will be going something like this, and at this value it will be coming equal to 0. So this is our graphical representation if they are supposed to find out. Next question. It states that find the electric field and the charge distribution that go with the following potential. Okay, so basic potential equation is given to us based on the value of this r, that is a distance, and r is governed by x square plus y square plus z square. Okay, and so first of all we will try to find out whether this particular relationship is our, or we are going to test a continuity at x r is equal to a. That is going to solve us. So we are going to check the continuity at r is equal to a. Continuity at r is equal to a. Okay. So it means we are going to make sure that the value of our potential to the left, inside and outside, whether they are same or they are different. So we have two equations. This is our first and this is our second. So in each equation we are going to substitute r is equal to a. Therefore we can say that for r is equal to a, and this we can call this as our inside because the point is inside the radius, and this point we can call this equation as our outside. So for r is equal to our a, we can write the inside for inside, we can say that our potential in at a distance a, and we simply substitute r is equal to a. Okay, so this we get this as rho naught 4 pi epsilon naught, and this is our a square. And then we solve for r is equal to a for outside. And once again we are going to put value of a, r is equal to a in our outside equation. So we get this as well potential out at a certain point a, and this will be coming as our rho naught 4 pi epsilon naught, and this is our minus a square plus it is our 2a cube upon a, and this a goes by q giving a square, so this will be minus a square and plus 2a square. Okay, and that will be giving us a square. Therefore from here we can say that our potential outside is equal to rho naught 4 pi epsilon naught and a square, and this is nothing but our potential inside. Okay, so it means there is a continuity between the potential inside and outside. Okay, this is the basically meaning of it. Okay, because if there would have been a different value of inside and outside, then we can say that there is a change in potential. Okay, or we can say there is a potential jump. Therefore from here we can say that there is a single well-defined value of potential inside and outside. We are having a single well-defined value of potential inside and outside. Therefore we can write that potential for a point r, okay, and that r is dependent upon our a, is continuous. is continuous at r is equal to a. And now we come to our main solution. Now we are required to find out our electric field. Therefore we can say that our electric field, our E of r, that is given as our phi, or we can also say it as a derivative of phi with respect to r, and direction is our r unit vector. Now once again, inside point as well as our outside point. So we can say inside, and inside giving us our r is less than a, and therefore we get that the change in potential will be equal to derivative, and that will be equal to our rho naught 4 pi epsilon naught, and derivative of this will be equal to our 2a, and a is equal to r, so that will be equal to our 2r. And so from here we can write that our electric field inside E in at a distance r will be minus rho naught 4 pi epsilon naught times 2r, and we can just simply, this goes by 2, so we get this as minus rho naught upon 2 pi epsilon naught r times r unit vector. Here also there should be r unit vector. Similarly we can do for our outside, and for outside r is greater than a, we can write our change in potential is equal to minus rho naught and derivative, so this will be 4 pi epsilon naught, and derivative comes as minus 2a cube upon r square. Therefore we can write our electric field out at a distance r will be equal to minus d phi upon dr r unit vector. We simply substitute the value, we get this as minus will be giving us plus, so this will be rho naught 4 pi epsilon naught, and here we have our a cube, or we can just cancel out our 2. Okay, so we can just put it here 2. So will be this a cube upon r square and our r unit vector. So we got the value of electric field as well as our inside and outside. Now we come to our charge density. Now charge density, we can use the standard relationship, which is our square of a potential is equal to minus density oblique epsilon naught, and which can be further written as, let me write it, which can be further written as our is equal to 1 upon r square d upon dr and r square potential and with respect to the distance. And now we once again come back to our inside point as well as our outside point. So we have our inside point, and for inside we know that value of r is less than a, and for that we know that the potential inside we just calculated is our rho naught 4 pi epsilon naught, and we have our r square. So we are simply going to derivate it. So we get our derivative of our potential will be equal to, this will be rho naught 4 pi epsilon naught, and this comes as our 2r. And major we are interested in creating this equation, so now we are going to multiply it by r square. Therefore we get this as r square potential inside, and this gives us our rho naught upon 4 pi epsilon naught, and this gives us 2r cube. Now we come to its derivative. We just generated half of it, and we are going to find out its derivative now. Okay. So we are going to find out its derivative. Therefore we get that our d of dr of our r square potential will be equal to, you can state for our derivative, this is our 4 pi epsilon naught and 6r square, and then we are going to divide it by 1 upon r square. Therefore we get square potential 1 upon r square and rho naught 4 pi epsilon naught 6r square, and here this r square and r square cancels out, and we can also cancel, this goes by 3 and this goes by 2. So therefore this will be equal to our, one second, something is missing. No, I think this is correct. So this is our 3 by 2 and rho naught pi epsilon naught, and we substitute in this equation. Therefore we get minus charge density upon epsilon naught is equal to 3 by 2 rho naught pi epsilon naught. This gives us the charge density inside will equal to minus 3 by 2, and epsilon naught cancel out, and this comes as our 3 by 2 times rho naught. And this is for inside point when value of r is less than a. Similarly, we can find out for our outside. Outside when of r is greater than a. And we already know that potential at the out is equal to our rho naught 4 pi epsilon naught minus a square plus 2a cube upon r. Okay. So first part is finding out its derivative. So we get our derivative of our out with respect to r. This will be coming as our rho naught 4 pi epsilon naught. Okay, and with respect to r, this will be equal to 0, and it will be coming as our r square, so minus 2a cube upon r square, and then we have to multiply it by r square. Therefore we can say our r square d phi out upon dr, and r square is going to cancel out, so this can as well rho naught 4 pi epsilon naught times minus 2a cube, and finally its derivative. So d of dr, our r square d phi out upon dr, and this entire term is constant, so we get from here is equal to 0. So it means our phi out is equal to 0, and this is nothing but our minus rho upon epsilon naught, and this is our out. Therefore we get that our rho out is equal to 0 for r greater than our a. So it means, and therefore we can say that there is a discontinuity at because of this surface charge, okay, because when it is less than a, it is having some value which is minus 3 by 2 upon rho naught, multiply by rho naught, and for greater than a it comes equal to 0. Okay. So means we can say from here that there is also a surface charge at r is equal to a, okay, because our electric field jumps or it has a different value. Okay. Therefore we can write, because of this discontinuity, we can say that our charge density will be equal to our epsilon naught electric field out minus electric field in. Okay. And these two both we are going to find out at r is equal to a. Therefore we get from here, we can say that our charge density at point A will be equal to our epsilon naught rho naught times A 2 pi epsilon naught plus rho naught A and 2 pi epsilon naught. So we can just add them and we get this as our pi naught A, rho naught A upon pi. Next question. So it is given a flat infinite non-conducting sheet lies in xy plane, z equal to 0. The only charges in the system are present on this sheet. In the region above the sheet, that is z greater than 0, the electric potential is given by this equation, where phi naught and k are the positive constants. Find the electric field, that E x of z, in the region z greater than 0, and surface charge density rho of x on the sheet at z is equal to 0. Okay. So this is also similar to the previous one, only difference is that here our potential is dependent upon x and it is also dependent upon our z. That is only difference. Okay. And so we are going to find out of electric field, and for the region z is equal to 0, and for that we are going to use the basic relationship that of electric field is equal to minus of our potential. And now from the given equation we know that our potential is dependent upon our x and it is dependent upon z. It is independent of our y. Therefore we can write out of our potential will be equal to partial derivative of potential with respect to x in x direction rather, plus potential in our z direction, and it is a k unit vector. Therefore from here we can write that the component of electric field in x direction will be our partial derivative of potential in our x direction, and there is no potential along y direction, so electric field along y will be equal to 0, and electric field in our z direction will be equal to minus partial derivative with respect over z. Now we are simply going to compute their partial derivative. And so first is our partial derivative with respect over x. And equation is already known to us. So we get this as our phi naught e raised to power minus kx kz minus kz and d of dx, and we have this as cos of kx, and this will be equal to over minus k phi naught e raised to power minus kz and giving us sine of kx. And we know that electric field is equal to negative of this. Therefore, we can say that electric field in x direction will be our minus of the partial derivative in x direction, which gives us a positive k phi e raised to power minus kz, and we are having sine of kx. And now we come to our z derivative. So we can say our partial derivative with respect to z will be equal to, this will be d of our dz phi naught e raised to power minus kz and multiply by cos of kx. And phi naught is our given as constant. Therefore, we can say that the partial derivative will be equal to minus k phi naught e raised to power minus kz and cos of our kx, and this will be equal to our negative of this. Okay. Therefore, we can say that electric field in z direction is negative of our the partial derivative. Therefore, we get the electric field in z direction will be equal to plus k phi naught e raised to power minus kz cos of our kx. Now we can just combine them. So we get the electric field in x and z direction will be equal to k phi naught e raised to power minus kz. We can take this as common and we get our sine of our kx I unit vector plus cos of kx k unit vector. And we have to remember this is for z greater than 0. And now we want to find out the charge density. Okay. And for that we are going to use the boundary condition along with the derivatives. Okay. We are already given that for z greater than 0, our potential that is dependent upon x and z is equal to our phi naught e raised to power minus kz cos of our kx. This is the given equation. Therefore, we can say that the normal component of electric field just above the sheet. So we can say that normal component of electric field just above the sheet. Above the sheet. Okay. And let us write it as our E positive z x comma 0. So this we get the partial derivative of our with respect to z at z is equal to 0. So let us compute the partial derivative, okay, and that we have already done also. So this comes as partial derivative with respect to z, which is our minus k phi naught e raised to power minus k z cos of kx. Now we have to find out at z is equal to 0. Therefore we can say that the partial derivative at z is equal to 0. And that is nothing but our electric field. So we can say electric field in z direction slightly above the sheet at z is equal to 0. Okay, we substitute z equal to 0. So this becomes 1. Okay, and we are having this as minus of, okay, so this will be minus minus plus, coming as our k cos of k times x. And for below the sheet, because we sorted out it our above the sheet, and then now we are going to do it for below the sheet. Below the sheet. But in the question, the equation of a potential is only given for z greater than 0. It means potential is just above the sheet. There is nothing below the sheet. Okay. Therefore, we can say that our value of our this below the sheet is there are no charges below the sheet. Basically, we can say from here. Okay. And therefore, we can say that electric field just below the sheet at x0 is equal to 0. Okay. Because whatever potential is there, that is at z greater than 0. Okay. There is nothing below the sheet. And so it means there is above the sheet the electric field is having some value, below the sheet is having a different value, no doubt that is 0. So therefore we can say there is some kind of jump in the electric field. So therefore we can use the boundary condition. So you can say boundary condition for a surface charge layer, and that is equal to our difference in the electric field above as well as our below. Okay. And that will be equal to our charge density divided by our epsilon naught. Okay. And we know for below the value is equal to 0, and for above we just found out. So we substitute the above value and we get this as our k phi naught cos of our kx minus 0 is equal to, and charge density, sorry, it is given as rho. So this comes as our rho of x upon epsilon naught. Therefore from here we are interested in charge density, that is our rho of x will be equal to epsilon naught k phi naught cos of our kx. Okay. This is the value of our charge density. So this completes all the 4 questions, and in today we try to solve the potential as well as our this electric field with respect to various types of equations. In the first part, we solved for the graphical representation of electric field, and from that graphical representation we derived the equations and then we solved the equations, whereas all the rest 3 questions, the equations were given to us and we solved the 3 questions based on the equations only. But we have to take care of the continuity. Okay, that's important point here, because in the first question, not the first question, I think it was second one, we found out that there is no discontinuity, whereas in this last 2 questions there was discontinuity. Okay, so because of this continuity and discontinuity, the entire formulation is going to change. Okay, so we have to keep this in mind. So this completes all the 4 questions. Thank you.